Hello, we are now ready for the ideal gas equation. So in 10.3, and by the way, this video is a chemistry video related to Chemistry, the Central Science by Brown, LeMay, Bursten, and Murphy, I believe. And although the ideal gas equation, I have a video in a physics series also on the ideal gas equation, but now we're ready for it in chemistry. And we've been building for it because in the previous section we talked about Boyle's law, we talked about Charles's law, we talked about Guy-Lussac's law. And so basically, previously on gas laws, Boyle's law basically says that the volume of something, say the volume of a balloon, is inversely proportional. This means is proportional to, that's what this symbol means. The volume is proportional to 1 over the pressure, or we say it's inversely proportional to the pressure. The pressure goes up, the volume goes down. Pressure goes down, volume goes up. And so that's called Boyle's law, after Robert Boyle, who lived in the 1600s. Okay, Charles, who lived in the 1700s, found that volume and temperature was directly proportional. So this is indirectly proportional, this is directly proportional. So if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. That's Charles's law. And then in the 1800s, we have Avogadro's law, which basically says that if the number of moles goes up, then the volume goes up. If the number of moles goes down, the volume goes down. So we have three kind of proportionalities here. Inversely proportional, directly, and directly proportional. Okay, so we can put these all together and say that volume is proportional to the number of moles times the temperature in Kelvin, we assume it in Kelvin, divided by the pressure. So there you have it. That's the combined proportionality. Now here's the thing. How do we get from this combined proportionality to an equation? Why, I'm glad you asked. The way that we do this in these sorts of sciences is we introduce a constant. They're proportional, but how do we make it equation? How do we make it equal? Well, we introduce a constant, a number that is multiplied by it. And now we have it. Volume equals the gas constant times the number of moles, the temperature in Kelvin, divided by the pressure. And so this is the way it's commonly expressed. P multiply through by P, and we get PV equals nRT. There you have it, the ideal gas law. Yay! Now, of course, there aren't any ideal gases exactly. I mean, helium, I think, comes close, but in general, the real gases are going to slightly differ a little bit, but there you have it. Now, what is the value of this gas constant R? Well, it kind of depends on what what particular units you're using. So if you're using liters, atmospheres, which is a unit of pressure we talked about in the second section of this chapter, moles, Kelvin, the chemistry book, in at least this chapter, is going to use 0.0832, blah, blah, liter atmospheres per mole Kelvin. However, the standard unit is more, and the physics book that I'm going through uses this particular units, 8.3 joules per mole Kelvin, or if you use pascals, 8.3 cubic meters pascals per mole Kelvin. Okay, so very important when you're doing problems is to make sure that you're using the right value of R, and that you're using that the units all agree with each other. Okay, there you have it. Now, it's common in chemistry to talk about STP. STP means standard temperature and pressure. Standard temperature is 0 degrees Celsius, or 270 degree Kelvin, and 1 atmosphere. Okay, that is the standard temperature and pressure. So if you say if something is at STP, you're going to assume that it's at this temperature and pressure. Now, at STP, 1 mole of an ideal gas will occupy 22.41 liters, and this is called the molar volume, because this is the volume that 1 mole of an ideal gas will occupy at standard temperature and pressure. Okay, something to tuck away for a rainy day or a voluminous day. Okay, so What happens if some of these factors are constant? So for example, what if the temperature is constant and the number of moles is constant? Then you don't need the whole equation, you just need part of it. So if the number of moles is constant and the temperature is constant, but you're varying the pressure and volume, then the before, pressure 1, volume 1, is going to equal the after, pressure 2, volume 2. And so you can leave out the middleman, leave out the number of moles, N, and leave out the gas constant, R, and leave out the temperature, T. You don't have to worry about those if the only thing that's varying is the pressure and the volume, okay? Or we can talk about what's called the combined gas law, where the number of moles is constant. Of course, R is a constant. Then we could say that P1 V1 over T1 equals P2. Okay, I made a mistake. So let me do a little magic here. Blink. Now it's right. So P1 V1 over T1 equals P2 V2 over T2. So if the number of moles is constant, then the pressure times the volume divided by the temperature before is going to equal the pressure times the volume over the temperature after. And so you can use this to amaze your friends with your mathematical and chemical skill. So there you have it, the ideal gas equation. Finally, at long last.